So today's webinar is building the largest solar smart array in North America. We're going to look behind the scenes of a 2.2 megawatt solar power plant. And our sponsors today are Talmage Solar Engineering, Tigo Energy, and Upsolar. You can learn more about their companies by visiting their sponsor profile page, which is linked to their logo from this webinar's page at principalsolarinstitute.org. Our moderator today is Kale Inoue. Kale is the Chief Financial Officer of Talmage Solar Engineering, and he was the developer of the Sharon, Vermont solar project. Since 1975, Talmage has had direct experience with all types of solar systems and equipment. And this gives them the knowledge they need to ensure years of trouble-free service for their customers. And we also have three panelists. Troy Dalbey is the Managing Director for North America from Upsolar, who supplied the solar panels for this project. Paul Grana is the Director of Product Management at Tigo Energy, who provided the energy maximizers. And Brad Sherman is the Technical Sales Rep for the Eastern region at Solectria Renewables, and they provided the inverters for this project. And with that, first of all, we will hear from Kale Inoue about the background and current status of this Sharon, Vermont solar power plant that he developed. So Kale, go ahead.
Thank you. So again, I'm Kale Inoue, Chief Financial Officer of Talmage Solar Engineering. I'm also one of the managing partners of SunGen, although we do have a slightly different ownership structure than Talmage, so it's not exactly a arm's length relationship. A couple things that we'll go over today: the basic structure of the difference between the EPC side and the development side, basic overview of what is up in Vermont, the equipment selection that we went through, and some of the reasoning behind that selection, a few of the key features of our array that sets it apart from others, a few of the challenges that we dealt with, certainly not all of them because that would be a much longer webinar, but just the ones that really stuck out, and then we'll do a quick Q&A at the end. So to begin, Talmage Solar Engineering is the EPC, the construction. EPC stands for Engineering, Procurement, and Construction. So the construction company that built the array. It's a family-owned business, started in 1975. In the beginning, we were much smaller back then, focusing on residential PV, solar hot water, wind, a little bit of hydro, and a bunch of off-grid systems. The industry has grown since then, and we've grown with it. We no longer do solar hot water, wind, off-grid systems. For the most part, we focus on just PV, and we try and keep our project size at least in the commercial scale or larger. We have completed over 2,000 projects. It's hard to gauge exactly how many because in the beginning the records were all on paper and nobody's willing to go through and count all of those, so that is an estimate. But we are a full-service EPC, so that means we do everything from the design, the engineering, the permitting, cost analysis. We do financial modeling. In the end, once we have a shovel-ready project, we can procure equipment, analyze the equipment that is being selected, and have reasons for that equipment. And then, of course, order it, meaning if it's in the U.S., we order, and we have trade lines that allow us to get the equipment on site. If it's an internationally produced product, then we work through the process of getting it here, which can be quite challenging. Once the equipment's on site, we can construct it using our crew that we have on staff. We do also hire seasonal laborers, but very little of our work is subbed out. So for the most part, that helps us control costs. It also makes it easier to ensure that we'll have a high level of quality. One of the things that we pride ourselves on is being able to be very efficient with the amount of people that are involved in the project. And although it seems like we have a very small staff, we're accomplishing what 3 times, sometimes 5 times as many people will be doing. And a lot of times we're doing it in half the time. I regularly follow other projects, and I'm continuously impressed with our field crew. So the other side of that is the development side, and this is entirely separate from Talmage. There's no common ownership. There's no hierarchical ownership. The owners of Talmage do own SunGen, but there are also other partners in SunGen. So that's a necessary structure for development in the U.S. Because of the tax incentives. The main driver for all of the projects in the U.S. right now are the ITC and the depreciation. They account for over half of the value of these systems. And more importantly, in the first 5 years, they're close to 80% of the revenue. So it's a very significant amount of funding that comes from tax equity. In order to make that work, you have to have a development company. SunGen is a generic name for all of the development projects that we do. So in this case, this is SunGen Sharon. It's because it's a SunGen project in Sharon, Vermont. But we also have about a dozen other projects that are in various locations around New England, all under generally the same structure. The difference is that by having individual project entities, we're able to bring in different partners for each project. We have been in operation under that model since 2007. I'd have to say that definitely the last 2 years has been significantly better for development. There's been some major changes in the industry as far as pricing goes, and that's really allowed this to take off. The incentives relative to the costs have actually come down, so it's been harder on the incentive side, but certainly the drop in cost has been what really is stimulating this growth and development. We have received, I believe it's 11 1603 grants, and for those of you who are aware of the 1603 grant, it's a cash grant in lieu of the ITC. Instead of getting a tax credit, which has to be monetized, the Treasury Department gives a dollar-for-dollar grant. That process can be very challenging, and for a lot of new developers, it's definitely one of the biggest unknowns because many people, even if they have experience in solar, haven't gone through the grant process. Also, for financiers, because it's a government program that's relatively new and relatively short-lived, there isn't a lot of experience with how to deal with that. And so, of course, we had to get around a lot of those financier concerns. But for the most part, we have a lot of trust in the program itself. I'd say it was the single most successful incentive that I've ever seen as far as getting massive volume out into the grid and also stimulating a lot of development. The Vermont SPEED program was initially conceived in 2009, and there were 14 awardees of projects in Vermont. It was the entire program was only 12.5 megawatts, and they had almost 300 megawatts of applications spread over almost 200 applicants. So it ended up being a lottery, and SunGen was lucky enough to get one of the projects, one of the biggest projects. The feed-in tariff program in Vermont was limited to 2.2 megawatts, so we did apply for the maximum size. At the time, it was the largest feed-in tariff program. This was before Ontario and after Gainesville, so kind of right in the middle of when feed-in tariffs were being brought around. one of the things that I ran into early on with the feed-in tariff pricing, because in Vermont it was 30 cents a kilowatt hour, was the perception that it was too low. And so bear in mind this is 2009 and costs are still around $6 a watt for retail install cost, and a lot of the developers and EPCs felt that the 30 cents a kilowatt hour was too low. The concept behind the feed-in tariff in Vermont was the long-term contract should allow for better financing, longer-term financing, longer amortization on the loan, and therefore a chance of actually being able to pull it off. And initially, I would say that may have been a misjudgment of what the financial world was willing to do, since there weren't any lenders giving 20-year loans on solar projects at that time. The things that changed were, of course, the industry matured very rapidly. In about 2 years, financiers got on board with lending on solar, and also the price came down dramatically. So we had at least 40% drop in cost, which was key to being able to make it work. Of course, the incentive didn't change, and the cost came down. So that was what brought the feed-in tariff program in line with what the incentive should have been. Also at the time was a push in New Jersey and Massachusetts to bring in the SREX model, which has a lot more volatility, but potentially is a much higher return for investors. And at least in 2009, 2010, there were a lot of developers that shied away from Vermont and went to New Jersey and Massachusetts. Of course, the problem with SREX, as we've all seen, is it's a market-based approach to the demand for SREX, and once that capacity is reached, the bottom falls out of the value very quickly. So over time, the Vermont feed-in tariff started to look a lot better because of the certainty in the contract. SunGen right now is privately held, and we have no plans of ever going public, but for the most part, we do plan on funding it ourselves. We don't have any corporate backing or another entity that we represent. So this is definitely a relatively slow bootstrapping process, and I don't expect us to explode and do 500 megawatts next year. So the project itself, as I mentioned, 2.2 megawatt DC nameplate. This was originally just an oversight by the Vermont lawmakers without knowledge of how solar nameplate really works. They just picked the number 2.2 megawatts and didn't actually designate whether it was DC or AC. And it turns out that in recent months they've determined that they meant to say AC, and they just left it undetermined. So we actually have the opportunity to expand our system by roughly 400 kilowatts, and there are plans for that in the works right now. The Vermont Speed Program is, as far as I can tell, the best incentive that's out there over time. It certainly has proved that it is able to be financed. It's proved that it can attract investors. It's proved that it's administered in a way that delivers certainty as well as a reasonable return. This site was in the CVPS, that's Central Vermont Public Service territory. They've since been acquired by Green Mountain Power, and in that area it's 12,000 volt, 1247 grid. So the radial feeders there are a little bit smaller than what we see in the rest of New England. The standard in Massachusetts, and most of New Jersey is a 13.2 grid. So that may be the reason that they ended up at the smaller number, slightly under the industry standard of 3 megawatts. We were able to find a site that was a 12-acre field. There were some topography issues that didn't allow us to use all of it. We ended up only having access to about 9 acres. So we were restricted by space, and we did have to pack it in, but there certainly was enough space there. We have it oriented due south, but there's also, because of the east-west run of the topography, there's also a slightly eastern tilt, which means we're getting morning sun rather than afternoon sun. But even with the slightly off due south orientation of that compound angle, we are expecting about 2.3 million kilowatt hours each year. And that's the minimum number. We, based on our modeling, are expecting that. Of course, modeling a lot of times takes into account worst case scenarios and maximum degradation. So I wouldn't be at all surprised if we outperform that in the first 5 years or so. Of course, as the degradation starts to kick in, we will see that number drop. But the 2.3 is pretty much all we needed to get it financed, and we had no trouble supporting that output with the conditions that were on site. The equipment that we chose, the Upsolar 230-watt panel. Keep in mind, when we started doing our design, that was late 2009, early 2010, and at the time, I think the most common panel was maybe a 210 or 220 for the 60-cell panel. We ended up making a change midway through that didn't require any change in our system impact study to be able to go up to a 230-watt panel, which was helpful in keeping costs down and also allowing us to have enough power coming out of that relatively small footprint. The panel that was chosen and the company that was chosen was mostly selected because of the business model of Upsolar, and I'll let Troy talk about that in more detail. But as we've seen recently, a lot of the Chinese manufacturers that are overladen with debt are in trouble, and Upsolar was not one of those. And I felt that they definitely have one of the best opportunities to actually be around for many years. As an EPC, that is important to us, but as a developer, that is essential to us. We definitely need to know that if there's a warranty issue, if there's a recall, even if there's a performance issue, that they will be around. And right now, panel manufacturers are either in trouble or, as we've seen recently, going out of business pretty frequently. And it seems like the size of a company is not relevant to the survivability. Some of the biggest companies in the industry have pulled out. It's more of a question of debt to equity, or the value of the company versus how much it's borrowed. I would advise any developer to look into their manufacturer, not based on the advertising that you've seen, and not based on what the big names in the industry are, but more on the quality of the panels, the quality of the warranty, and the stability of the company behind it. That's going to serve you better in the long run. There are EPCs out there that are pushing very low-cost panels, and the argument for it is, if the upfront cost is low enough, you buy extras, and if they go out of business, then you just replace them. Unfortunately, when those projects actually get built, of course, nobody wants to buy extra equipment, and so that theory is blown out of the water. We're into cutting a corner today to potentially get it financed and in the future end up not being able to pay the loan because of an equipment failure. Solectria inverters were used. We ended up using 19 of the PVI 95s. Again, this was a decision that was made in 2010, and so the cost and the field testing of the larger inverters that we see today, the 500s and the 250s, it certainly didn't have as much momentum behind it as today. We did have to make a decision on inverters when we applied for our interconnection, so once that was in place, it couldn't be changed. Well, it could be changed, but couldn't be changed without a lot of additional time and money. So the 19 inverters that we used should provide us at least enough stability and enough history to be able to sell their uptime to a bank. And I say sell, but I mean convince a bank that this critical component of the array, this linchpin, is not going to fail and is not going to cause us to be unable to produce for a significant amount of time. Inverters are the one thing in the array that can break you in a very short period of time if you pick the wrong one. If you pick an inverter that fails and is impossible to service or impossible to get parts, and your loan is tied directly to production, you will have trouble if you have the wrong inverter. So we've worked with Solectria for years and feel that they're definitely, at least as far as inverters go, on the leading edge. Tigo was a late add to the game. We ended up adding them after our system impact study was done, and I'll let Paul talk more about their maximizers, but they do have a unique value-added proposition. We used aluminum wire, which is somewhat discouraged in a lot of circles, but because we increased the size of the wire, in some cases several times over what was needed, there was no safety issue. And the racking was a Terrafix design, which involves an earth screw and then 3 in portrait. The rack lengths actually vary quite a bit. So some of the unique features of this, of course, as I mentioned, the feed-in tariff 2.2 megawatts is the largest available size in Vermont. But this site is a utility scale site, but using a lot of commercial features, the 95 kilowatt inverter and the 60 cell panel were chosen because of their tested reliability in the field. The Tigo energy part was the add-on that potentially could have separated us from the other 2.2 megawatt projects in Vermont, and their increased performance, although it hasn't been tested at this scale, was enough of a potential gain to have us take a serious look at it and actually take a risk on installing them. We ended up only installing Tigo on 90% of the panels in the field, and 10% were installed without Tigo maximizers. So we will have the opportunity to compare performance at the same site with the same inverters, with the same weather features. Everything will be a fair experiment, and we'll be able to see if there's actually an increase in performance. We did have a lot of challenges with this site and with the Vermont permitting in general. Vermont doesn't have any local permitting for solar or really any renewable energy projects. They do go through the state, and the permit required is the 248 permit. So it's the same permit for all energy generation, whether it's Vermont Yankee or a 5 kilowatt system. And that was really what separated a lot of the developers. lot of the developers. All of the small ones dropped out when they found out that they were looking at several $100,000 of permitting cost. At this site, we had limited ground space, so of course we were packed in, but we also, because it was on a field that was under agricultural preservation, we weren't able to contour the land. So we had to find a solution that allowed us to deal with the topography without a lot of excavation. We had a limit of 1 acre that we were allowed to disturb. Interconnection, again, in Vermont, it's a smaller grid. It's also an older grid, and in a lot of places, because of the low population density, it is very susceptible to big generators coming online. So we did have to do a fair amount of upgrades, probably the most upgrades that I've seen in any site, and that's all due to the population density and the lack of load on the grid. Financing was obviously a challenge, and for any solar project, it is a challenge. We were able to finance with 2 separate banks, a local bank for the permanent piece in Vermont and a construction lender during construction. Both of those took different positions, and they were independent of each other, but they did work together quite well. They only came into the picture in 2011. Prior to that, there were no options for financing. Our data feed is a huge problem, or was a huge problem. Initially, we had to be on a cell connection because there was no high-speed internet in the area, and of course, all the reporting that we're looking at, all the data coming out of the each individual panel and each individual inverter was too much for the cell connection. Since then, we've been able to convince Fairpoint to give us a DSL connection, so that's been solved. And of course, in Vermont, if anyone's ever been to Vermont, they know that the weather there is extreme, both in the winter, extremely cold, and in the summer, extremely hot. There were certainly days that it was below 0 with our crew on site, all bundled up, and there were also days that it was close to 100 in the middle of the summer. So those were challenges that a lot of people don't think of when they're designing a project, but a crew that can't perform is going to make the rest of the project very difficult, and usually one of the main reasons that you're not able to perform in the field is weather. So that's the basic overview. I'm going to let the individual manufacturers talk about the components in more detail, and of course I'll answer questions as much as I can.
All right, Kale, thank you very much for that. Just in the interest of time, we're going to collect the questions to the end to make sure we can hear from all of the suppliers. So again, chat your questions, send them to all panelists in the lower right corner of your screen. And Troy, I've made you the presenter, and so I'll have to ask you to kind of pick up the pace a little bit. You'll have about 6 minutes now. So Troy, go ahead.
No problem at all. Happy to be brief. My name is Troy Dalbey. I'm the managing director at Upsolar America. I've been with Upsolar for nearly 3.5 years. Was one of the original employees that opened up the U.S. market. Was formerly an American sales manager and was promoted to managing director about close to 2 years ago, I guess. It feels like yesterday. Anyway, just to give you a brief overview, one of my top team members, Stuart Schoenfield, had a history and had a relationship previously supplying Talmage when he was at Shot, and was was obviously, I know that Talmage was a big BP component back in the day, and it was very fortuitous that when BP was beginning to exit out of the out of PV, that we were able to initiate some meetings and leverage Stuart's existing relationship with Talmage, and They were very open to hearing Upsolar's value proposition, getting to really know the company, gain an understanding of our business model, and just to give you just a brief summary of that. Upsolar, while everyone else in our industry, particularly those who are China-based, have been in a rush to try to become as vertically integrated as possible, Upsolar focused instead on identifying key components, on making sure that those components were tested at our R&D center, which is about a 40,000 square foot R&D center in Shanghai, China. Has all of the types of testing equipment that you would see at a IEC or UL certified testing facility. So we've really focused on identifying top quality components. We control our supply chain, but we actually outsource the assembly of our modules, and it's done under our quality control team's supervision. But by doing so, we've been able to have a very, I'd say, a very flexible production output. We haven't had to continue to overproduce to keep people employed or to service debt that we have hanging over our heads on capital equipment and facilities and whatnot. So something that people maybe saw as a liability a couple of years ago, banks certainly see as an asset today. We have a very clean balance sheet, very little debt. We have debt ratios in about the 50% range, and our current or quick ratio is about 1.8 to 1, which is indicative of good financial health, both in the short term and the long term. As Kale had indicated previously, we had discussed supplying the project prior to our relationship with Tigo. Over the past year or so, we've worked with Tigo on the final stage of development of their smart junction box, and have recently just certified the industry's first smart module, and are actively out manufacturing that, and we're actually anticipate probably about between 7 and 8 megawatts of sales of 60 and 72 self-smart modules in Q4 this year. So we're very excited about that. The relationship with Tigo, we feel that it's a top quality product, and that they are certainly, in my opinion, the #1 optimizer or module level electronics provider in the industry. The reason that we suggested that to Talmage that they consider using the smart modules or an optimized solution, rather, because it wasn't certified at that point in time, was because of, as you can see in this picture, the hilly terrain. You have a situation where you would have modules on the same string, which would be on a different plane. On a typical string, you would go to the lowest common denominator and drag down the entire output of a string. Because of the fact that the array is optimized, you're going to get the maximum output out of each and every module, regardless of whether or not they're on the same plane or facing the same direction. And it's very important, as Kale just mentioned. It's the profitability of a project and hitting the target IRRs are predicated upon maximum output and generating all the electricity you possibly can out of the array that you're constructing. So what this was able to do is provide Talmage the flexibility needed to develop the project and to make it a profitable project as well. We're looking forward to working with Talmage on future projects as well, and have really pressed to see that they utilize a smart module on future projects as well. And we're really excited about this one in particular because of the fact that you have 10% of the modules being standard, and you have a beta. You effectively have a beta sample to be able to compare the output of the optimized modules versus standard modules, and I think it's going to make a really neat white paper in about a year or so. Some of the benefits of a smart module are the fact that you're going to obviously maximize your energy output. You're going to have increased design flexibility. You really truly eliminate any mismatch that can exist between output of modules within a string, and you have a flat IV curve because of the voltage control that the module level electronics bring to this situation, and so you're actually able to increase the number of modules per string between 20 and 25%, which is going to help you save on your BOS. And what we really like about it as well is the fact that you have module level monitoring, MPPT tracking, and you're able to. It really makes, like for a project like Talmage, it's going to make the O&M much more simple moving forward. Within the integrated junction box, you've got electronic theft prevention, and it's actually NEC 690.11 compliant and has arc fault protection built into it. The impact is about 10 cents a watt on a 240 watt module, about 8 cents a watt on a 290 watt module or a 72 cell format. As you can see, one of the neat things about this is you can take a look at it at an array. If there's a problem with the module, if everything is good, green is go. If you've got an issue and you have a poor performing module within a string, you're going to get a yellow indication. If there's a serious issue with the module, it's obviously going to be red. You can go straight to the specific module that you see where the issue is. You're able to do so without having to go through combiner level or string level diagnostics, and really just able to do it as efficiently and as effectively as possible. As I said before, the incremental cost of the smart junction box to our modules is between 8 and 10 cents. You're looking at initially at a 5 cents per watt reduction in your balance of systems costs. You're able to get more modules on any roof or situation because you can deal with shading issues quite easily, and don't have to worry about, as I said previously, having arcing issues or diode issues within those modules that do encounter shade from time to time. You've got increased energy harvest, and we were able to vet that and gain an understanding of it on our test array, where we've been testing Tigo's technology for over a year now in Shanghai. We've seen an increase in unshaded situations in the 3 to 4% range versus the beta array, and in various types of shaded situations, up to 11% increased output of an optimized module versus a standard module. Just to give you a quick brief background of Upsolar's BOM, or the components that go into our modules, we're very proud of our components list. This is something that you will very rarely see in the PV industry. A lot of people like to claim black box on what it is that goes into their modules. I think that I'm of the opinion that if you are using good solid equipment, you're going to have to make a good solid module that's going to be built to last 25 years. We have 2 separate BOMs that are certified in case we have an issue in the supply chain, but effectively use either Pilkington or CSG glass. We use Huber Schooner as a standard junction box. we now have the Tigo Smart Junction Box, which we use and have the option, if a customer would like it, to provide a Tigo junction box. In the U.S. market, we almost use exclusively MC4 connections, never knockoffs, always the best components money can buy. Typically, we use either Kemple or kilowatt backsheets. Since the issue with the countervailing and dumping that has come up, we have switched our cell suppliers for the U.S. market to Upsolar and the Motec. We use Bridgestone, Sandvik, EVA, and either Corning or Tungsten silicon gel. And I can't emphasize enough how important it is that the gel that a module supplier uses, and the back sheets and the EVA, the things that don't have logos that you can't tell, are the most important parts of your BOM in surviving 25 years and being able to honor warranty. We never set out to make a high output module. At Upsolar, the whole goal is trying to create a module with the best quality to price ratio in the market, which I do believe that we provide. But nevertheless, if you do use top quality components, you're going to have a high quality module. And as you can see, Upsolar at Photon's test array has the number 6 and 7 performing module this year. And being outperformed by SunPower is to be expected, I think, but we can come in at a price point that's roughly 60% of what SunPower does. So for the additional output that you receive, I think that you're going to be certainly paying for it and then some. The Upsolar modules that are in the array there were all installed in 2010 and 2011. You have Yingli that just had a module installed in 2012 that is outperforming us, and I think that you can see there's one from Solar World and one from CMPV as well. But I would also say that we are much more competitively priced than those vendors, and I think that we have a much more stable and healthy balance sheet than anyone else on that list, or any other Bloomberg New Energy Finance Tier 1 module supplier. And just once again, the Smart Junction Box is going to provide string level monitoring, anti-theft security, intelligent alert in the event of potential theft, excellent fleet management, and the ability to retrofit with the add-on optimizers if need be. And I will.
Yeah, thank you very much, Troy. In the interest of time, questions are coming into the chat, and I'll have Troy answer those out to chat to all participants, and we'll chat the question back to all participants first also. And Paul, we'll go ahead and make you the presenter, and I know we're running late. We're going to extend this about 15 minutes. Several participants have asked for that. So Paul, you have about 7 minutes. You can go ahead and begin.
All right, thanks very much. Again, I'm Paul. I run product management at Tigo Energy. I'll keep it relatively crisp here because I think Kale and Troy have already hit on a number of the key points for our involvement here. To start with a little bit of background, I'll talk a bit about how we work because, frankly, we're not a standard part of a solar system yet. In a couple of years, we'll be on a majority of solar arrays, if not the almost full majority of all arrays, which I can talk about some of that upcoming code changes. But today, us and any other module level electronics is still a new part of the system. As you can see on the chart here, we put a small circuit board into the back of a solar module, which is up until recently is a bolt-on box, and that product is still available. But as Troy mentioned, we now have a UL listed fully smart module with the PCB embedded into that junction box. So that's, as you can see here, with that partial cutaway of that junction box with our circuit board inside. Having electronics on the back of each module will give a number of benefits. First of all, you get more energy because we can keep each module working at its individual peak power point. Second of all, we provide module level data, which leads to a lower cost O&M because now truck rolls can be scheduled more optimally. The crews know right where the problems are. And you can often do advanced troubleshooting remotely, so you don't even need a person on site to help diagnose what the nature of a problem is. And then finally, we enable a safety shutoff mechanism, which I'll talk about at the end. But basically, it's a low-voltage shutoff, which is actually part of the code requirements for 2014. So we're ahead of the curve, as is Talmage ahead of the curve, on offering a lot of the safety and anti-islanding benefits of a low-voltage shutoff that isn't mandated yet, but actually will be mandated soon. So in terms of how it works, we have a maximizer behind each module, and again, it's that circuit board that you saw on the previous screen. And those also work together with something called a management unit. Now, the key aspect here is that a lot of the brains are actually put into the management unit rather than having them behind a module. And that's actually the way that we're able to design the most scalable architecture. Essentially, you don't want a full computer behind every solar module. It's actually a bit of overkill. Our approach is to essentially minimize the amount of hardware you have on a single module. On a small scale, that's only a nice talking point, but on a large scale, when you've got a 2.2 megawatt array, that is an absolute design necessity. You can't have part counts in the hundreds of components on that board when you've got that on 9,000 modules throughout the array, such as we've got here. So instead, we've got the brain centralized at these management units, and those are responsible for essentially controlling the behavior of the maximizer and collecting data and sending that back. And then, of course, we also offer software, both web-based platforms and smartphone-based platforms that help the owner and developers, in this case Talmage and SunGen, get the most of that module-level data, so they can essentially see it from anywhere in the world, use some of our advanced tools online to dig in if there's some sort of anomaly. Now, the reason that our system is special, and frankly, the reason that I would think that the Talmage folks chose us instead of a microinverter, in addition to the fact that microinverters aren't sort of nearly as commercial scale as a maximizer, is that if you're doing the math in terms of cost, efficiency, and reliability, which are really the most important things, you know, there are secondary things about being able to install one module at a time. But again, when you've got 9,000 at once, you don't really mind, you know whether you can have a 3-module array. If you want a 3-module array, then microinverters are great. But if you've got anything that's larger than a full string, a system with a maximizer and a best-in-class central inverter is going to give you a much better cost structure, efficiency structure, and reliability profile. The other key point here is that if in terms of actual reliability, which Kale's already mentioned a bit, in terms of reliability, we've got the only product in terms of module-level electronics that can actually have a benign failure mode. So 95% of the failures, if one of our pieces on the board goes down, 95% of the time we result in a module that still produces power. So, you know, if you're putting stuff behind a module, such as this circuit board you see here on the right, you don't want that pulling down that entire 230-watt solar module. So that's actually a key design attribute that we've got that really no microinverter can really offer. Now, people have talked about the mismatch in an array. We've seen the waviness that was on this array at Talmage. In addition to that, there's generally a few points, a few percentage points, I should say, of soft sources of mismatch, and we call them soft because, you know, there's also a whole class of mismatch due to shade. If you've got, if you're on a commercial roof and there are obstructions, or if you're in a ground mount array with a nearby tree line, then there can certainly be sources of mismatch from hard shade. But even when you don't have hard shade, there are differences in irradiance due to high altitude clouds, differences in irradiance because modules in the edges of the array run at a cooler temperature than the modules in the center of an array, mainly because you've got different wind loads at those corners of the array. And that leads to a few percent energy loss due to mismatch without Tigo. And then subsequently, when you can have the maximizers in that array, we can earn that energy yield back. Here on the right, you're seeing actually a shot of some data from NREL. So this is, you know, we like using this data set because it's, even though Tigo's got a whole bunch of data, people generally don't trust us, which, you know, that's fine. But you know, we've all got to trust NREL. This is a case where they had 17 light meters near a single array in Hawaii, and on average there was a 15% standard deviation throughout the year. So That's basically mismatch because of clouds and also secondarily because of soiling on that array. So we can earn back a bit of energy, and it might not be, you know, the 10 to 30% that people initially thought of with microinverters, but that's just because there's just no magic. You know, if you're talking 30% energy harvest, it's because you've got a tree sitting right in front of your whole array. In most well-designed arrays, the opportunity is between about 3 and 7%. In addition to that, as we've talked about, and I'll kind of go quick here, because we can control the power point of each module, when you've got these sort of designed-in mismatch, in order to maintain the integrity of the field here and not grade it, we're able to make up for that mismatch and prevent that from harming the production of the array. And then now in terms of module level data, Troy had a great slide, you know, showcasing a commercial scale system. Here I actually want to dive deep a bit. In terms of module level data, one of the things that's really special about the Maximizer system is that we've got data at 2-second increments. Most data loggers are doing 15 minutes. And the difference between 2 seconds and 15 minutes is huge. In this case, and this is actually not an Upsolar module, so I want to point out, you know, we've seen extremely low problems, in fact, probably arbitrarily close to 0 on the Upsolar stuff that we've been installed with. But this is a different module type in a different array entirely. And you'll notice here that on this one specific day, this is in the summer of 2010, there was an overpower event where for a brief moment these two 40-watt modules were generating nearly 300 watts of power. That raised the current to a point where the solder connection between these cells became overheated and started to arc. So actually, you can actually see when we went out to the field to investigate this, the arc had shattered the front glass and had burned a hole through the back sheet. Because again, if you don't have a perfect uniformity in the solder connections, you can have problems on your array. Some of which would either, at the very least, hurt the power production and potentially cause an unsafe situation. With our module level data, we can actually see the pattern of what's happening. So if you've got a problem, we can generally tell the difference whether it's a low voltage arc, or a bird that died and just happened to land on your module, or some other sort of weather-related problem. And then finally, as I've made reference to a couple times, the last benefit of having module-level electronics is that we can shut off each module individually. The way systems are designed today, there are disconnects at the end of every string. So when you hit the disconnect, there's no current flowing, there's no power being generated. However, there is a voltage potential. So in this simple example, if you've got 10 modules with a 60-volt open circuit, then that open circuit's got up to 600 volts there. Which again, where that becomes a problem is if you've got a firefighter or maintenance workers, they could inadvertently make those conductors cross, and then suddenly you've got a burst of power that's waiting to happen, and those are lethal voltages. When you've got maximizers on the array, we're shutting off every single module. So if there are cables between each module and the Tigo maximizer, then you may have 60 volts at that individual pair of cables, but that's a much more benign voltage than 600 volts. And then there's no voltage in series, so those cables home are going to be at 0 volts the whole time. And as I said, that's a very nice benefit today because you can make sure that your maintenance workers and any emergency workers are always going to have a safe environment. But this type of shutoff, making sure the system is below 70 volts, that's actually how the code is written. That's drafted to be passed in NEC 2014. That's in the U.S. Canada is also looking at a similar concept. And again, these are basically to protect firefighters and to provide an extra layer of anti-islanding to prevent grid and utility workers when they're operating on an array. So this is where the industry is going. We can, because of products such as Tigo, we can raise the bar in terms of safety, so that the industry can actually proactively make sure that we're always doing the right thing to make sure that we've got a very sustainable industry that both has good performance, but also has the sort of cost-appropriate safety measures. So yeah, with that, I will pass it over.
Okay, thank you very much. And again, in the interest of time, we'll be answering questions through chat, and I will turn things over to Brad. And Brad, go ahead. You can begin.
All right, great. Thanks very much. So my name is Brad Sherman. I'm with Solectria Renewables. I cover sales for the East Coast here. So we've been working with Kale and the team at Talmage for a number of years. and this was one of the larger projects we've worked on with them. So with that, I'll give a quick background on Solectria Renewables. We were a company that was founded in 1989 as an electric vehicle manufacturer. We sold off that division of the company, focusing on electric vehicles in 2005, and founded Solectria Renewables, which is the inverter manufacturer. And as you can see through this timeline here, we've since been bringing just kind of larger and a more broad spectrum of products to market since then. Most recently, larger utility-grade products like a 500 kilowatt inverter and multi-megawatt power stations. The 95 kilowatt inverter that was utilized on the Sharon project has actually been in service for quite a while, for about 7 years. So it was kind of a tested and true product, and that was the product that we went with for this project. So here's a couple photos of the array that we've kind of seen before, and I'll go through the products that were utilized on Solectria's end. So obviously inverters, that's our main business model. Solectria Renewables is first and foremost an inverter manufacturer. We also do a number of side products like string combiners for balance of systems. SolarEnView is our monitoring interface. And then, as Kale mentioned, the inverters end up being probably the most sensitive and unique component in the system, and as such, they wanted to put some performance guarantees on the inverter. So in this deal, we worked out what's called an uptime guarantee on the inverters, which is essentially a guarantee of a certain percentage. Usually it's 99 or 99.5% of inverter uptime is guaranteed by us, by Solectria, the inverter manufacturer, to the owner of the system. So in the event that downtime that's allowable is exceeded, then Solectria actually is under contract to reimburse the owner at a fixed reimbursement rate. So we have an uptime guarantee in place on this project. It was part of helping Kale and the team sell it to the bank, and it's actually something that we are increasingly seeing in the inverter market moving forward. So kind of a unique model. It's pretty highly customizable, and that was one of the benefits that Solectria is able to offer that led to this project. So the inverters, here's a photo of the inverters they're stationed kind of scattered throughout the array. Part of the reason for doing that was to minimize the DC wire runs. So as Kale mentioned, the 95 kilowatt inverter was chosen instead of larger central inverters for a number of reasons. One of them would be lower DC wire runs, but also added redundancy throughout the array. So if you've got 18 inverters or 19 inverters, that's many more points of, a much higher level of redundancy. So if there's ever an issue, you're only losing one small fraction of that array. That's compared to a 500 kilowatt inverter. If that inverter were to go down, then you'd be losing a lot more power production. Now, that being said, we've added a number of features to our 500 kilowatt inverter to actually ensure uptime and redundancy within the inverter itself. So we have it such that if there ever is an issue, there are actually three power stages, essentially 3 inverter drives inside a 500 kilowatt inverter to alleviate that concern. But for this project, we went with smaller inverters, and that was what they were comfortable with. So we were fine to support that. And so this is just a look of the inverter. It's a pretty industrial-looking inverter. They're made in the U.S., so we make all of our inverters in Lawrence, Massachusetts, where we've got about 1 gigawatt of annual production capacity across all of our main inverter lines. And they're pretty rugged pieces of equipment. These are all located outside. They're NEMA 3R rated for outdoor use, and obviously these are having to withstand some pretty substantial weather environments up in Vermont. So we've got a number of units deployed even farther north, up in northern Ontario, participating in the feed-in tariff up there. So from a weather and kind of a longevity standpoint, we fully warranty the equipment to be installed in locations such as this. So some of the balance of systems components that we provided were string combiners. We have a number of string combiner options, but this is a standard version, but we're seeing the industry, because of code changes, moving toward a disconnecting string combiner box. And we have those options available now as well. So basically a DC disconnect located right on the string combiner. And we're also coming out with some more options to add some intelligence to the combiner boxes, like smart combiners with string level monitoring and arc fault protection for future code purposes. So taking kind of a quick look at what Solectria's value proposition was for the Sharon, Vermont project. In general, when we look at what we believe the inverter value proposition is summarized as, we look at performance, reliability, serviceability, and flexibility of the inverter design. Obviously, with performance, the first thing you're going to look at is efficiency and operating voltage windows. So Solectria has market-leading CEC efficiencies pretty much across the board. A wide-range MPPT window, maximum power point tracking window, which in this case actually wasn't as big of a selling feature once you got the Tigo maximizers in there, because obviously Tigo maximizers significantly increase the inverter's ability to optimize maximum power points. So that was a big benefit of the Tigo maximizers on this project. Reliability. So we were founded in 1989. We've been building inverters for over 20 years, working with Talmage for quite a while. So obviously they were comfortable to use Solectria inverters, but in general, the technology that spun off from the electric vehicles is still used in the inverters today, and it's a pretty streamlined technology process that results in about 25 to 50% fewer electrical connections inside the inverter itself. So every electrical connection is essentially an additional point of failure. So we're able to limit that inside our inverter design. And just kind of from an array level, redundancy using multiple inverters versus single central inverters was an added benefit for reliability and overall uptime of this project. And lastly, obviously, there was a performance guarantee. So we're contractually obligated to perform at a certain level, which is a nice insurance policy for a project of this size. And like I said, something that we're seeing more and more in the industry today. Serviceability, so we have the ability to really easily train third-party service providers because of the simplicity of Solectria's inverter design. So we can train folks at our EPCs like Talmage to perform Tier 1 level service if there ever is an issue. In addition to that, we have a number of service hubs located throughout the North American area, and of course, out of Massachusetts, we're right about 2 hours south, so we're very close to the Sharon, Vermont project in particular. And 24/7 system monitoring, they chose SolarEnview web-based monitoring to go along with this project, and that way we have 24-hour surveillance on the inverter's performance. And lastly, flexibility. So Solectria has a lot of options and features and customizations available on the inverters, and we were flexible enough in this case to work with the Tigo maximizers and basically ensure system compatibility for the long term. So that's pretty much it.
Thanks a lot, Brad. That was we're running 5 minutes over the hour, 20 minutes past our original time, but this information is really good. I'm going to take just 2 questions. The first one, maybe Troy or Paul can clarify Kale's chat. Is the smart module now listed to both UL 1703 and UL 1741?
Yes, it is.
It is? Okay, excellent.
Upsolar is, yes, I should say.
For Upsolar?
Both the 60 and 72 cell format, mono and polycrystalline.
Okay, great. And this question is for Paul or Brad. How does the maximizer system work with the Solectria inverter? Did it have to be configured any particular way?
This is Paul. I can start with that. We generally, and as far as I believe in this case is the same, generally don't require any change at the central inverter at all. You can think of how we work as a current balancing device, making sure that when modules have a mismatched max power current, a mismatched IMP, we're essentially boosting the current on the weak ones so that the strong modules set the string current. That's kind of a basic principle of operation. But so really, at a high level, we make sure that the whole array looks like the strong modules in the array, instead of having the weak ones pulling down and making that IV curve become very lumpy and nonlinear. So there's no constant voltage aspect to it. There's no special inverter settings. We work great with Solectria inverters, but we're also inverter agnostic. So, for example, with Upsolar's modules, they don't have to, commit to a single inverter manufacturer.
Yeah, and to that point, Solectria here has worked with a number of DC, kind of optimization technologies, and I've got to say the Tigo one is really, really nice in that there really is nothing special that we have to do out of the box on the inverter. At least not nearly to the extent of some of the other devices that are out there that are basically putting out in some cases a constant DC voltage that's preset, and then the inverter has to operate outside of MPPT, so we have to turn off MPPT. So that's not the case with Tigo. We just right out of the box, it's pretty much a standard device. So that was really important to us in making this a pretty streamlined process.
Okay, and then just one last question, then we'll end. So what is the actual listing on the JBox integrated module, both 1703 and 1741, or is it something else?
The module is the 1703. I believe the junction box is the 1741. Yes, Paul?
Yep, that's correct.
And does Tigo address AFCI?
So it's actually a much longer discussion. We could probably spend an hour, but I'll give you a 30-second version. There are two types of ARCs, series and parallel. We have our series ARC product in UL right now, so we have not yet finished 1699B, so I can't say that we satisfy that. But when we do, then obviously we expect that within just a couple months. That's for series ARC. Parallel ARC is mandated in 2014, so we will have a product before 2014 for that, but that's probably in sort of realistically a 2013 product release is to have parallel ARC detection. So it's actually a broader than a pure disconnect. But then in terms of the actual system disconnect and shutoff, we already satisfy the module level shutoff, which is the sort of higher caliber of deactivating an array, which is an option in 2011 and mandated in 2014. So there's actually three pieces. There's low voltage shutoff, series ARC detection, and parallel ARC detection.
All right, and that'll end everything. We don't have any more time for questions, but I will leave the chat window open. If you continue to chat questions, I'll get those to our presenters, and we'll include them in the email tomorrow. Thank you very much to all four of our panelists, and thank you for our audience for attending. Again, this will be recorded. It will be available tomorrow at principalsolarinstitute.org. And while you're there, you can visit the companies that you have seen here to see their contact information and learn more about them. Thank you.